Hello. Welcome to the Bore You to Sleep podcast. The podcast that will hopefully help you get to sleep. I am going to read an open source book, one that is not particularly interesting, but one that is hopefully boring enough to get you to sleep. Tonight's readings comes from The Modern Clock, a study of timekeeping mechanism, its construction, regulation and repair. Written by Ward L. Goodrick, this book is an instruction manual for any good apprentice that wants to become a clockmaker or repairer. Written in 1905, I must admit they don't make clocks and watches like they used to. My name is Teddy, and I aim to help people everywhere get a good night's rest. Sleep is so important, and my mission is to help you get the rest you need. Each episode is designed to play in the background while you slowly fall asleep. The podcast is completely free, and it's the support from listeners that allows me to keep bringing out more episodes. I want to thank a bunch of special listeners for their words of kindness this past week. iTunes listener BRAUSR, Nancy and Avalon for your lovely messages via the website, Alice and Emily May for your shout-outs on Instagram. It means so much to me that the podcast is helping all of you get the rest that you need. If the podcast helps you, please subscribe and leave a review. It really does help out. You can also say hello and support the podcast on Patreon at boreyoutosleep.com. I'm also now on Twitter and Instagram at boreyoutosleep. In the meantime, lie back, relax, and enjoy the readings. Chapter 1. The Necessity for Better Skill Among Clockmakers. The need for information of an exact and reliable character in regard to the hard-worked and much-abused clock has, we presume, been felt by every one who entered the trade. This information exists, of course, but it is scattered through such a wide range of publications and is found in them in such a fragmentary form that by the time a workman is sufficiently acquainted with the literature of the trade to know where to look for such information, he no longer feels the necessity of acquiring it. The continuous decrease in the prices of watches and the consequent rapid increase in their use has caused the neglect of the pendulum timekeepers to such an extent that good clockmen are very scarce, while botches are universal. When we react that the average life of a worker at the bench is rarely more than 20 years, we can readily see that information by verbal instruction is rapidly being lost, as each apprentice rushes through clockwork as hastily possible in order to do watchwork, and consequently each watchmaker knows less of clocks than his predecessor, and is therefore less fitted to instruct apprentices in his turn. The striking clock will always continue to be the timekeeper of the household, and we are still dependent upon the compensating pendulum in conjunction with the fixed stars, for the basis of our timekeeping system, upon which our commercial and legal calendars and the movements of our ships and railroad trains depend, so that an accurate knowledge of its construction and behavior forms the essential basis of the largest part of our business and social systems, while the watches for which it is slighted are themselves regulated and adjusted at the factories by the compensated pendulum. The rapid increase in the dissemination of standard time and the compulsory use of watches having a maximum variation of 5 seconds a week by railway employees has so increased the standard of accuracy demanded by the general public that it is no longer possible to make careless work go with them, and if they accept it at all, they are apt to make serious deductions from their estimate of the watchmaker's skill, and immediately transfer their custom to someone who is more thorough. The apprentice, when he first gets an opportunity to examine a clock movement, usually considers it a very mysterious machine. Later on, if he handles many clocks of the simple order, he becomes tolerably familiar with the time train, but he seldom becomes confident of his ability regarding the striking part, the alarm and the escapement, chiefly because the employer and the older workmen get tired of telling him the same things repeatedly, or because they were similarly treated in their youth, and consider clocks a nuisance anyhow, never having learned clock work thoroughly, and therefore being unable to appreciate it. In consequence of such treatment, the boy makes a few spasmodic efforts to learn the portions of the business that puzzle him, and then gives it up, and thereafter does as little as possible to clocks, but begs continually to be put on watchwork. We know of a shop where 2 and sometimes 3 workmen are constantly employed upon clocks, which country jewellers have failed to repair. If clock work is dull, they will go upon watchwork, and they do good work too, but they enjoy the clocks and will do them in preference to watches, claiming that there is greater variety and more interest in the work than can be found in the fitting factory made material into watches, which consist of a time train only. 2 of these men have become famous, and are frequently sent for to take care of complicated clocks, with musical and mechanical figure attachments, tower chimes, and etc. The third is much younger, but is rapidly perfecting himself, and is already competent to rebuild minute repeaters and other sorts of the finer kinds of French clocks. He now totally neglects watchwork, saying that the clocks give him more money and more fun. We are confident that this would be also the case with many other American youth, If he could find someone to patiently instruct him in the few indispensable facts which lie at the bottom of so much that is mysterious, and from now which he now turns in disgust. The object of these articles is to explain to the apprentice the mysteries of pendulums, escapements, gearing of trains, and the whole technical scheme of these measures of time, in such a way that hereafter he may be able to answer his own questions, because he will be familiar with the facts on which they depend. Many workmen in the trade are already incompetent to teach clockwork to anybody, owing to the sliding process above referred to. The frequent demands for a book on clocks have therefore induced the writer to undertake its compilation. Works on the subject, nominally so, at least are in existence, but it will generally be found on examination that they are written by outsiders, not by workmen, and they treat the subject historically, or from the standpoint of the artistic or the curious. Any information regarding the mechanical movements is fragmentary, if found in them at all, and they are better fitted for the amusement of the general public than for the youth or man who wants to know how and why. These facts have impelled the writer to ignore history and art in considering the subject, to treat the clock as an existing mechanism which must be understood and made to perform its functions correctly, and to consider cases merely as housings of mechanism, regardless of how beautiful, strange, or commonplace those housings may be. We have used the word compile advisedly. The writer has no new ideas or theories to put forth, for the reason that the mechanism we are considering has during the last 600 years had its mathematics reduced to an exact science, its variable factors of material and mechanical movements developed according to the laws of geometry and trigonometry, its defects observed and pointed out, its performances checked and recorded. To gather these facts, illustrate and explain them, arrange them in their proper order, and point out their relative importance in the whole sum of what we call a clock, is therefore all that will be attempted. In doing so, this free use has been made of the observations of Saunier, Reid, Glasgow, Ferguson, Britton, Riefler, and others in Europe, and of Jerome, Platner, Finn, Learned, Fersen, Howard, and various other Americans. The work is therefore presented as a compilation, which it is hoped will be of service in the trade. In thus studying the modern American clocks, we use the word American in the sense of ownership rather than origin. The clocks which come to the American workman today have been made in Germany, France, England, and America. The German clocks are generally those of the Schwarzwald, or Black Forest district, and differ from others in their structure, chiefly in the following particulars. The movement is supported by a horizontal seat board in the upper portion of the case. The wooden trains of many of the older type, instead of being supported by plates, are held in position by pillars, and these pillars are held in position by top and bottom boards. In the better class of wooden clocks, the pivot holes in the pillars are bushed with brass tubing, while the movement has a brass scape wheel, steel wire pivots, and lantern pinions of wood with steel trundles. In all these clocks, the front pillars are friction tight, and are the ones to be removed when taking down the trains. Both these and the modern Schwarzwald brass movements use a sprocket wheel and chain for the weights and have exposed pendulums and weights. The French clocks are of two classes, pendules and carriage clocks, and both are liable to develop more hidden crankiness and apparently causeless refusals to go than ever occurred to all the English, German, and American clocks ever put together. There are many causes for this, and unless a man is very new at the business, he can tell stories of perversity that would make a timid apprentice want to quit. Yet the French clocks, when they do go, are excellent timekeepers, finely finished and so artistically designed that they make their neighbours seem very clumsy by comparison. They are found in great variety, time, half-hour and quarter-hour strike. Musical and repeating clocks begin a few of the general varieties. The pendulums are very short, to accommodate themselves to the artistic needs of the cases, and nearly all have the snail strike instead of the count wheel. The carriage clocks have watch escapements of cylinder or lever form, and the escapement is frequently turned at right angle by means of bevel gears, or contrate wheel pinion, and placed on top of the movement. The English clocks found in America are generally of the Hall variety, having heavy, well-finished movements with seconds, pendulum, and frequently with calendar and chime movements. They, like the German, are generally fitted with weights instead of springs. There are a few English carriage clocks fitted with springs and fuses, though most of them, like the French, have springs fitted in going barrels. The American clocks, with which the apprentice will naturally have most to do, may be roughly divided into time, time alarm, time strike alarm, time calendar, and electric winding. The American factories generally each make about 40 sizes and styles of movements, and case them in many hundreds of different ways, so that the workman will frequently find the same movement in a large number of clocks, and he will soon be able to determine from the characteristics of the movement what factory made the clock, and thus be able to at once turn the proper catalogue if the name of the maker be erased, as this frequently happens. The comparative study of the practice of different factories will prove very interesting, as the movement comes to the student after a period of prolonged and generally severe use, which is calculated to bring out any existing defects in construction or workmanship, and having all makes of clocks constantly passing through his hands, each exhibiting a characteristic defect more frequently than any other, he is in a much better position to ascertain the merits and defects of each maker than he would be in any factory. Having thus briefly outlined the kinds of machinery used in measuring time, we will now turn our attention to the examination of the theoretical and mechanical construction of the various parts. The man who starts out to design and build a clock will find himself limited in three particulars. It must run a specified time. The arbor carrying the minute hand must turn once in each hour. The pendulum must be short enough to go in the case. Two of these particulars are changeable according to circumstances. The length of time run may be 30 hours, 8, 30, 60, or 90 days. The pendulum may be anywhere from 4 inches to 14 feet, and the shorter it is, the faster it will go. To one definite point in the time train is that the minute hand must turn once in each hour. We build or alter our train from this point both ways, back through changeable intermediate wheels and pinions, to the spring or weight forming the source of the power, and forward from it through another changeable series of wheels and pinions to the pendulum. Now, as the pendulum governs the rate of the clock, we will commence with that and consider it independently. The natural laws governing pendulums. A pendulum is a falling body, and as such is subject to the laws which govern falling bodies. This statement may not be clear at first, as the pendulum generally moves through such a small arc that it does not appear to be falling. Yet if we take a pendulum and raise the ball by swinging it up until the ball is level with the point of suspension, and then we let it go, we shall see it rapidly fall until it reaches its lowest point, and then rise again until it exhausts the momentum it acquired in falling, when it will again fall and rise again on the other side. This process will be repeated through constantly smaller arcs until the resistance of the air and that of the pendulum spring shall overcome the other forces which operate to keep it in motion, and it finally assumes a position of rest at the lowest point nearest the earth, which the pendulum rod will allow it to assume. When it stops, it will be in line between the center of the earth, that's the center of gravity, and the fixed point from which it is suspended. True, the pendulum bob, when it falls under control of the pendulum rod, and has its actions modified by the rod, but it falls just the same, no matter how small its arc of motion may be, and it is this influence of gravity, that force which makes any free body move toward the Earth's center, which keeps the pendulum constantly returning to its lowest point, and which governs very largely the time taken in moving. Hence, in estimating the length of a pendulum, we must consider gravity as being the prime mover of our pendulum. The next forces to consider are mass and weight, which, when put in motion, tend to continue that motion indefinitely, unless brought to rest by other forces opposing it. This is known as momentum. A heavy bob will swing longer than a light one, because the momentum stored up during its fall will be greater in proportion to the resistance which it encounters from the air and the suspension spring. As the length of the rod governs the distance through which our bob is allowed to fall, and also controls the direction of its motion, we must consider this motion. Referring again to the previous discussion, we see that the bob moves along the circumference of a circle, with the rod acting as the radius of that circle. This opens up another series of facts. The circumference of a circle equals 3.1416 times its diameter, and the radius is half the diameter, the radius in this case being the pendulum rod. The areas of circles are proportional to the squares of their diameters, and the circumferences are also proportional to their areas. Hence, the lengths of the paths of bobs moving along these circumferences are in proportion to the squares of the lengths of the pendulum rods. This is why a pendulum of half the length will oscillate 4 times as fast. Now we will apply these figures to our pendulum. A body falling in vacuo in London moves 32.2 feet in 1 second. This distance has, by common consent among mathematicians, been designated as the G. The circumference of a circle equals 3.1416 times its diameter. This is represented as pi. Now if we call the time t, we shall have the formula t equals pi over 1 divided by g. Substituting the time, 1 second for t, and doing the same with the others, we shall have a different formula. Turning this into its equivalent in inches by multiplying by 12, we shall have 39.1393 inches as the length of a 1 second pendulum at London. Now, as the force of gravity varies somewhat with its distance from the center of the Earth, we shall find the value of G in the above formula varying slightly, and this will give us slightly different lengths of pendulum at different places. Having now briefly considered the basic facts governing the time of oscillation of the pendulum, let us examine it still further. The pendulum shown here has all its weight in a mass at its end, but we cannot make a pendulum that way run a clock because of physical limitations. We shall have to use a rod stiff enough to transmit power from the clock movement to the pendulum bob, and that rod will weigh something. If we use a compensated rod so as to keep it the same length in varying temperature, it may weigh a good deal in proportion to the bob. How will this affect the pendulum? If we suspend a rod from its upper end and place alongside of it our ideal pendulum, we shall find that they will not vibrate in equal times if they are of equal lengths. Why is that? Because when the rod is swinging, being stiff, a part of its weight rests upon the fixed point of suspension, and that rod is consequently not entirely subject to the force of gravity. Now, as the time in which our pendulum will swing depends upon the distance of the effective center of its mass from the point of suspension, and as, owing to the difference in construction, the center of mass of one of our pendulums is at the center of its ball, while that of the other is somewhere along the rod, they will naturally swing in different times. Our other pendulum, the rod, is of the same size all the way up, and the center of its effective mass would be the center of its weight, if it were not for the fact which we stated a moment ago, that part of the weight is upheld and rendered ineffective by the fixed support of the pendulum rod. All the while the pendulum is not in a vertical position. If we support the rod in a horizontal position, as we did by holding up the lower end, the point of suspension, it will support half the weight of the rod. If we hold it at 45 degrees, the point of suspension will hold less than half the weight of the rod, and more of the rod will be affected by gravity, and so on down until we reach the vertical or up and down position. Thus we see that the force of gravity pulling on our pendulum varies in its effects according to the position of the rod, and consequently the effective center of its mass also varies. It varies with its position, and we can only calculate what this mean or average position is by a long series of calculations and then taking an average of these results. And that concludes tonight's readings. I hope you're feeling a little drowsy. If you're still awake, please feel free to listen to another episode. In the meantime, I'll be bringing you another episode very soon. Good night.